Hi, hello there. Good day. Welcome to Data Link Layer. Every network has physical components and media connecting the components. Different type of media needs different information about the data in order to accept it or move it across the physical network. So think of it this way. A well-hit golf ball moves through the air fast and far. It can also move through water, but not as fast or as far unless it is helped by a more forceful hit. So this is because the golf ball is traveling through a different medium, water instead of air. So data must have help to move it across different media. The data link layer provides this help. As you might have guessed, this help differs based on the number of factors. So this module gives you an overview of these factors, how they affect data, and the protocols designed to ensure successful delivery. Let's get started. Okay, so for the module objective, so at the end of this video lecture, you should be able to explain how media access control and data link layer protocols supports communication across network. So subtopics includes the purpose of the data link layer, topologies, and the data link frame. So let's start with the purpose of the data link layer. So the data link layer of the OSI model, this is on layer 2, okay, so from this stack or protocol stack, okay, prepares the network data for physical network. So the data link layer is responsible for network interface card to network interface card communications. So the data link layer does the following. So enables the upper layer to access the media. The upper layer protocols is completely unaware of the type of media that is used to forward the data. It accepts data, usually layer 3 packets, example IPv4 or IPv6, and encapsulates them into a layer 2 frames. So it controls data, okay, placed and received on the media. Exchanges frames between endpoints over the network media, receives encapsulated data, usually layer 3 packets, and directs them to the proper upper layer protocols. So it also performs error detection and rejects any corrupt frames. So in computer networks, a node is a device that can receive, create, store, or forward data along a communication path. A node can either an end device, such as laptop, mobile phone, or an intermediary devices such as Ethernet switch. So without data link layer, the network layer protocol such as IP would have to make provisions for connecting to every type of media that could exist along the delivery path. So additionally, every time a new network technology or medium was developed, okay, so it would have to adapt to it. So the figure here displays an example of how data link layer adds layer 2 Ethernet destination and source NIC information to a layer 3 packet. So it would then convert this information to a format supported by the physical layer. Example is the layer 1. Okay, so if you can see in this diagram here, so you've got the layer 2 and layer 3. Okay, so that would be forwarded from the NIC of this workstation PC1 to the web server. Okay, now the layer 2 header appended the destination NIC and the source NIC. We're talking about the MAC address here. Okay, so the destination MAC address or the physical address and the source MAC address or the source physical addresses. Now on the layer 3 packet, you also have the source and destination addresses. So we call it an IP address. Okay, so on a layer 3 packet, the layer 3 appended the header and it has the source IP and the destination IP. So the source IP is basically the IP address of PC1, which is 192.168.1.110. Okay, and the destination IP is 192.168.1.5 with that of the web server. Okay, now for the destination MAC address here, this pertains to the MAC address of the source or of PC1. Okay, so that would be the source NIC. Now the destination NIC is, of course, whoever is connected to it. For example, you have the router there in between, then that would be the destination NIC. All right. Okay, so the IEEE 802 LAN or MAN standards are specific to Ethernet LANs. Okay, so wireless LANs or WLANs, wireless personal area networks or WPAN, and other types of local and metropolitan area networks. So the IEEE 802.X, okay, specifically the 802.2 and 802.3, okay, which pertains to the logical link control and the media access control. Okay, now the IEEE 802 LAN MAN data link layer consists of the following two sublayers, which I have mentioned earlier. That pertains to the logical link control or LLC and the media access control or MAC. Okay, now when you say logical link control or LLC, this IEEE 802.2 sublayer communicates between the networking software at the upper layers and the device hardware at the lower layers. Okay, so LLC is situated here. As what I've said earlier, it is capable of communicating to the upper layers, okay, network layer and app, and to the hardware on the MAC sublayer down. Okay, so it places the information in the frame that identifies which network layer protocol is being used for the frame. So this information allows multiple layer 3 protocols such as IPv4, IPv6, okay, to use the same network interface and media. So the next one is the media access control. Okay, this sublayer implements in hardware. Okay, so this is under 802.3, okay, 802.11 or 802.15. Okay, so it is responsible for data encapsulation and media access control. It provides data link layer addressing, and it is integrated with various physical layer technologies. Okay, so would it be on the Ethernet 802.3, 802.11, which is the wireless, and the WPAN, which is 802.15. So the LLC sublayer takes the network protocol data, which is typically an IPv4 or an IPv6 packet. And then it adds layer 2 control information to help deliver the packet to the destination node. So the MAC sublayer controls the NIC and other hardware that is responsible for sending and receiving data on a wired and wireless LAN or MAN medium. So the MAC address sublayer provides data encapsulation. Okay, and these are the frame delimiting, addressing, and error detection. Okay, so when you say frame delimiting, the framing process provides important delimiters to identify fields within a frame. So these delimiting bits provide synchronization between the transmitting and receiving nodes. Addressing provides source and destination addressing for transporting the layer 2 frame between devices on the same shared medium. And the last one is error detection. It includes a trailer used to detect transmission errors. So the MAC sublayer also provides media access control, allowing multiple devices to communicate over the shared or in half duplex medium. So full duplex communication do not require access control. All right. Okay, so providing access to media. So each environment or network environment that packets encounter as they travel from local host or remote host can have different characteristics. For example, an Ethernet LAN usually consists of many hosts contending to access or for access on the medium. Okay, so the MAC sublayer resolves this. With serial links, the access method may only consist of a direct connection between only two devices. Okay, usually two routers, for instance. So therefore, they do not require the techniques developed or employed by the IEEE 802 MAC sublayer. So router interfaces encapsulates the packet into an appropriate frame. So suitable media access control method is used to access each link. So in any given exchange of network layer packets, there may be numerous data layers or data link layers and media transitions. So at each hop, along the path, a router performs the following layer 2 functions. So first, it accepts a frame from the network medium. And then it encapsulates the frame to expose the encapsulated packet. Third, it re-encapsulates the packet into a new frame. And last, it forwards the new frame appropriate to the medium of that segment of the physical network. So the router, is capable of encapsulating and de-encapsulating also, same with the data link layer. So every layers on the OSI model has what you call protocol data unit. And in the data link layer, we call it frames. In the network layer, we call it packet. On the transport layer, we call it segments or datagrams. All right. Okay, let's talk about the purpose of the data link layer. So the data link layer protocols are generally not defined by request for comments or RFCs, unlike the protocols on the upper layers of the TCP/IP suite. So the Internet Engineering Task Force or IETF maintains the functional protocols and services for the TCP/IP protocol suite in the upper layers, but they do not define the functions and operations of the TCP/IP network access layer. Right? So the engineering organization that define the open standards and protocols that apply to the network access layer, example, the OSI physical and data link layers, includes the following. So I know you're familiar with some of this organization, like the IEEE or the Institute of Electrical and Electronics Engineers. You also have the ITU or the International Telecommunications Union, the ISO or the International Organization for Standardization, and the ANSI or the American National Standard Institutes. So the logos of this organization are shown in the figure here. Okay, so next is topologies. So we have two types of topology. So it's either physical topology or logical topology. So as you learned in the previous topic, the data link layer prepares the network data for a physical network. It must know the logical topology of a network in order to be able to determine what is needed to transfer frames from one device to another. So this topic explains the ways in which the data link layer works with different logical network topologies. The topology of the network is the arrangement or relationship of network devices and the interconnections between them. So that's topology. So there are two types of topologies, as I have mentioned earlier. These are the physical and logical topologies. Now, what's the difference between the two? So when you say physical topology, it identifies the physical connections and how end devices and intermediary devices, example, routers, switches, and wireless access points are interconnected. The topology may also include specific device locations such as room number, location on the equipment rack. So physical topologies are usually point-to-point or star topology. When you say logical topology, it refers to the way a network transfers frames from one node to the next. So this topology identifies the virtual connections using device interfaces and layer 3 IP addressing schemes. The data link layer sees the logical topology of the network when controlling data access to the media. It is the logical topology that influences the type of network framing and media access control used. Now I have here a diagram of a physical topology. The figure displays a sample physical topology for a small sample network. So the physical network topology shows 6 rooms. All right. So you'll have here the server room at 2158, room 2124, right? 2125, 2126, 2127, and 2159. Okay. Now it contains a router labeled R1. Right. We've got R1 here on rack 1, shelf 1. Okay. So a cable at the top connects to the cloud, labeled as the internet. So this is how you present a physical logical topology. Okay, so everything is labeled in accordance with the rack, the shelf, the role, if it is a web server, an email server, or a file server. Okay. Now for logical topology, okay, so the same network, the logical network topology shows devices, right? Same devices as presented earlier, but we don't care about the location. Since this is logical topology, we want to show the IP addresses as shown here. The role is in there, the ports used by the devices or the interfaces of the device. Okay, so also if you will observe, there is no room indications or indicators here. All right, so rooms are represented by a network address now. So you've got network 192.168.10.0 on this area. Now going back to the previous slide, that is the server room. So server room at 2158 in logical topology, it is just represented by a network address. And same thing with the rest of the rooms here. All right. So that's the difference between the physical topology and the logical topology. Okay, so how about WAN topologies? So the figures illustrate how WANs are commonly interconnected using a 3 common physical WAN topologies. So this includes a point-to-point, hub and spoke, and mesh topology. So when you say point-to-point, okay, point-to-point is the simplest and most common WAN topology. It consists of a permanent link between 2 endpoints as what you see here. So for instance, we have 2 routers here directly connected to each other, maybe via a serial cable. This is an example of point-to-point connection. Okay, so the next one is hub and spoke. Okay, so also known as, or popularly known as, the star topology. All right, so the hub and spoke, this is a one version of star topology in which a central site, okay, so we call it a hub, interconnects branch sites through the use of the point-to-point links. So branch sites cannot exchange data with other branch sites without going through the central site. Okay, so the problem with this is if this central site goes down, then all of these branch sites are disconnected. All right. So the third one topology is what we call a mesh topology. Okay, so one site is directly connected with each other. So this topology provides high availability but requires that every end system is interconnected to every other system. So therefore, the administrative and physical costs can be significant. So each link is essentially a point-to-point link to the other node. Okay, so a hybrid is a variation or combinations of any of this topology because we have that. Now you can combine any of these 3 common physical topologies to come up with what you call a hybrid version. Okay, so for example, a partial mesh is a hybrid topology in which some, but not all, end devices are directly connected to each other. Okay, how about point-to-point WAN topology? Okay, so physical point-to-point topologies directly connect 2 nodes. Okay, so as shown in the figure. In this arrangement, the nodes do not have to share the media with other hosts. So additionally, when using a serial communication protocol such as point-to-point or PPP, a node does not have to make any determination about whether an incoming frame is destined for it or another node. So therefore, the logical data link protocols can be very simple, as all frames on the media can only travel to or from the 2 nodes. The nodes places the frames on the media. At the end of those frames are taken from the media by the node at the other end of the point-to-point circuit. Okay, so note that a point-to-point connection over Ethernet requires the device to determine if the incoming frame is destined for this node. So a source and destination node may be indirectly connected to each other or in some geographical distance using multiple intermediary devices. However, the use of physical devices in the network does not affect the logical topology, okay, as illustrated in the figure here. Okay, so this is an example of a point-to-point physical topologies. Okay, so the logical point-to-point connection is the same. Okay, next. How about LAN topologies? So from your basic networking courses, maybe you have heard of these terms. Okay, so in multi-access LANs and devices, example nodes are interconnected using star or extended star topologies, as shown in the figure here. So I've got star topology, okay, and extended star. You just interconnected star topology. Okay, so in this type of topology, the end devices are connected to a central intermediary device. In this case, it's an Ethernet switch. Okay, now the star and extended topologies are easy to install, so very scalable, easy to add and remove end devices, and easy to troubleshoot. Early star topologies interconnected end devices using the Ethernet hubs, but nowadays we are using switch. Okay, so at times there may be only two devices connected to the Ethernet LAN. An example is two interconnected routers. Okay, this would be an example of an Ethernet used on a point-to-point topology presented earlier. Okay, you also have what you call the legacy LAN topologies. So early Ethernet and legacy token ring LAN technologies included two other types of topologies. Okay, so which you often heard, okay, less on this time, which are the bus topology and the ring topology. So bus topology, as you can see in the diagram, okay, all the end systems are chained to each other and terminated in some form on each end. Okay, so they are terminated by a terminating resistor or TR. Okay, the legacy Ethernet networks are often bus topologies using coaxial cables because it was inexpensive and easy to set up. Okay, so as far as I remember, during my time, right, during our training days, when we implemented bus topology, it has a maximum of 10 workstations only. All right. So the next one is a ring topology. End systems are connected to their respective neighbor, forming a ring, as what you can see here. Okay. So the ring does not need to be terminated. Unlike in bus topology, we do terminate end nodes or end connections. Okay. So legacy fiber distributed data interface, or the FDDI, and the token ring networks used ring topologies. Okay. Now the figures illustrates how end devices are interconnected on the LAN. So it is common for a straight line in networking graphics to represent an Ethernet LAN, including a simple star and an extended star. Okay. All right. So the next one is the operation of half and full duplex communications. Okay. So understanding duplex communication is important when discussing LAN technologies or topologies, because it refers to the direction of data transmission between two devices. So there are two common modes of duplex. Okay, so you've got the half duplex and full duplex. All right. So actually we have the first one, which is called simplex. Okay, simplex is a communication wherein it is unidirectional and it always goes through the client. Okay, so an example of that is a radio station or a television. All right. So the direction is from the television to the end user. That's simplex, and the end user cannot respond to it. All right. So we are going to focus our discussion here on the half duplex and full duplex communication. So when you say half duplex communication, both devices can transmit and receive on the media, but cannot do it simultaneously, as what you see here on this animation. All right. So it is always from the hub to the server at a time, or from the server to the hub. Okay. So they cannot do it simultaneously. It is one at a time. That's the characteristic of a half duplex communication. Okay. So wireless LANs and legacy bus topologies with Ethernet hubs use the half duplex mode. So half duplex allows only one device to send or receive at a time on the shared medium. Okay, so observe the animation here. The data is either from the server to the hub or from the hub to the server. Okay, now on a full duplex communication, both devices can simultaneously transmit and receive on the same shared data or same shared media. Okay, so the data link layer assumes that the media is available for transmission for both nodes at any time. So Ethernet switches operates in full duplex mode by default, but they can operate also in half duplex if connected to devices such as the Ethernet hub. Okay, so in half duplex, it's mainly used in an Ethernet hub connectivity. All right, but nowadays, since we are using Ethernet switches, so we are now in a full duplex communications wherein the server and the switch here can simultaneously send data. So it is important that two interconnected interfaces such as a host NIC and an interface on an Ethernet switch operate using the same duplex mode. That's the recommendation. All right. So if you made the duplex here in full, then on the other end, it should also be full duplex. Okay. So otherwise, there will be a duplex mismatch, creating inefficiency and latency on the link. All right. Okay. So access control methods. Ethernet LANs and wireless LANs are examples of multi-access networks. A multi-access network is a network that can have two or more end devices attempting to access the network simultaneously. So some multi-access networks require rules, okay, to govern how devices share the physical media. There are two basic access control methods. Okay, this is applied on the shared media. So these are the contention-based access and the controlled access. Okay, so we will be discussing this on the next slide. So let's start with the contention-based access. So under the contention-based, we have two. All right, so we've got the CSMA CD, or the carrier sense multiple access with collision detection, and CSMA CA, okay, carrier sense multiple access with collision avoidance. So CSMA CD is used on a legacy Ethernet LAN. So if you are using a wired LAN, it uses a CSMA CD. Okay. Now in contention, okay, in contention-based multi-access networks, all nodes are operating in half duplex, competing for the use of the medium. However, only one device can send at a time. Therefore, there is a process if more than one device transmits at the same time, for example. Okay, so examples of contention-based access methods includes the following. Now you've got the carrier sense multiple access with collision detection, or CSMA CD, as what I've said, applied on a legacy Ethernet LANs, and the CSMA CA, which is applicable for wireless. All right. So next is CSMA CD uses a collision detection process to govern when device can send and what happens if multiple devices send at the same time. So there's what you call data collision. All right. So if two devices happens to send data at the same time on the cable or on the medium, it would lead to collision. Okay. And therefore, this function here has what you call a carrier detection feature. Right. Now, CSMA CD collision detection process. So once there is a collision, So this is what will happen, right? So devices transmitting simultaneously will result in signal collision on the shared media. So devices detects the collision, since you have here the collision detection feature, and devices wait a random period of time and retransmits the data. That's how it works on CSMA CD, right? If again that happens, that all the workstations send data on the cable at the same time, then it has to go through with this process, right? So the workstations are persistent in sending data. All right, so let's have some detailed explanation here. Okay, so contention-based access using CSMA CD. So basically, that would start with the PC1. Okay, so PC1 has an Ethernet frame to send to PC3. Okay, now the PC1 NIC needs to determine if any device is transmitting on the medium. So if it does not detect a carrier signal, in other words, it was not receiving transmission from other device, it will assume the network is available to send. Okay? And then the PC1 NIC sends the Ethernet frame when the medium is available, as shown in the figure here. Alright? So the assumption here is that the cable is available for use, and therefore PC1 has sent the frame on the cable. Okay? Next, the hub receives the frame. The Ethernet hub receives and sends the frame. An Ethernet hub is also known as the multi-port repeater. So any bits received on the incoming port in here, okay, that would be generated and sent out on all the ports as shown in the figure. So take note that the data is for PC3. Right? The data should be forwarded to PC3, but the hub will forward that to all the computers connected on the hub or on the device. Okay? So if another device such as PC2 wants to transmit but is currently receiving a frame, it must have to wait until the channel is clear. Alright? And then the last phase is the hub sends the frame. Okay? So all devices attached to the hub will receive the frame as shown in the diagram. However, because the frame has a destination data link address for PC3, then only that device will accept and copy the entire frame. All other devices, NICs or network interface cards, will just ignore the frame as that of PC2. Okay, so according to PC2 here, this frame is not for me, so I will just ignore it. That is because of the destination MAC address. All right. Okay, so another form of CSMA, okay, used by IEEE 802.11, which pertains to the wireless LAN, is the carrier sense multiple access with collision avoidance. All right, CSMA CA. Okay, now the CSMA CA uses a method similar to CSMA CD to detect if the media is clear. CSMA CA uses additional techniques. In wireless environments, it may not be able or possible for a device to detect a collision. Okay? The CSMA CA does not detect collisions but attempts to avoid them by waiting before transmitting. So each device that transmits includes the time duration that it needs for the transmission. So all other wireless devices receive this information and know how long the medium will be unavailable. Right? So it uses avoidance rather than detection. Okay? So on this figure here, host A is receiving a wireless frame from the access point. All right. Host B and C will also see the frame and how long the medium will be unavailable. Okay. So after a wireless device sends an 802.11 frame, the receiver returns an acknowledgement so that the sender knows the frames arrived. Okay. So whether it is an Ethernet LAN using hubs or a wireless LAN, contention-based systems do not scale well under heavy media use. Okay, so but then nowadays, Ethernet LANs using switches do not use a contention method system because the switch and the host NIC is operating on the full duplex mode. Okay. All right. So the next one is the controlled access. So in controlled-based multi-access network, each node has its own time to use the medium. So these deterministic types of legacy networks are inefficient because a device must wait its turn to access the medium. So again, today, Ethernet networks operate in full duplex and do not require an access method. Okay, so this legacy controlled access includes token ring and the legacy ArcNet. When we say legacy, so it is almost not existing. Okay, it's obsolete already. Okay, so the next one would be the data link frame. Okay, so remember, I have mentioned earlier that every layer on the OSI model has a PDU or the protocol data unit. Okay, so on the physical layer, we call it bits. On the data link layer, we call it frame. Okay, on the network layer, we call it packets. Transport layer, we call it segment or datagram. All right. And on the application layer, of course, that is in a data form. Okay. Now, on this part or on this segment, we are going to focus on the protocol data unit on the data link layer, which is called frame. Okay. Now, this topic discusses in detail what happens to the data link layer frame as it moves through the network. So the information appended to a frame is determined by the protocol being used. So the data link layer prepares the encapsulated data, usually an IPv4 or IPv6 packet. Okay, so for transport across the local media by encapsulating it with a header and a trailer to create a frame. So the data link layer protocol is responsible for NIC to NIC or NIC to NIC communications within the same network. Although there are many different data link layer protocols that describe data link layer frames, so each frame type has three basic parts. All right. So basically, it has the header, the data itself, and the trailer. Okay. So unlike other encapsulation protocols, the data link layer appends information in the form of a trailer, okay, at the end of the frame. So all data link layer protocols encapsulates the data within the data field of the frame. However, the structure of the frame and the fields contained in the header and trailer vary according to the protocol. All right? Okay. So there is one frame structure that meets the needs of all the data transportation across all types of media. So depending on the environment, the amount of control information needed in the frame varies to match the access control requirements of the media and logical topology. For example, a wireless LAN frame must include procedures for collision avoidance and therefore requires additional control information when compared to an Ethernet frame. Okay, so as shown in the figure here, in a fragile environment, okay, more controls are needed to ensure delivery. The header and trailer fields are larger as more control information is needed. So greater effort is needed to ensure delivery. So this means higher overhead and slower transmission rates. Okay. Now the frame fields comprises of these components. Okay. So framing breaks the stream into a desirable or decipherable groupings. So with control information inserted in the header and trailer as values in different fields. So this format gives the physical signals a structure that are recognized by nodes and decoded into packets at the destination. So the generic frame fields are shown in the figure here. Okay. And Not all protocols include all these fields. The standards for the specific data link protocol defines the actual frame format. All right. So basically, this is how it looked like, okay, on the protocol data unit on the data link layer, which is the frame. Okay. So you've got the packet, which is the data coming from the network layer. And then that data coming from the network layer will be appended with the header and the trailer once it reaches the data link layer. Okay. Now, what do you have on the header? Okay. The header basically has the source and destination MAC address. And the error control mechanism is on the trailer. Okay. Now, let's get into the details about what we have here on the subcomponents of the headers and the trailer. Okay. So let's start with the frame start and stop indicator flags. Okay. So the first component here. It is used to identify the beginning and end limits of the frame. Okay. Addressing indicates the source and destination nodes on the media. So we're talking about the source MAC address and the destination MAC address. Okay. Now for the type, it identifies the layer 3 protocol in the data field. And then control, it identifies special flow control services such as the quality of service. QoS, or quality of service, gives forwarding priority to certain types of messages. For example, voice over IP. Okay, so these frames are normally received priority because they are sensitive to delay. Okay, the next is data. Data is basically the actual data. It contains the frame payload. Okay, and the last one is the error detection. It includes or included after the date to form the trailer, and this is where the system can check whether there is or there are errors in transmission. Okay, now the data link layer protocols add a trailer to the end of each frame, so we call it trailer here. Okay, in a process called error detection, the trailer determines if the frame arrived without error. So it places a logical or mathematical summary of the bits that comprise the frame in the trailer. So the data link layer adds error detection because the signals on the media could be subject to interferences, distortion, or loss that would substantially change the bit values that those signals represent. So transmitting the node creates a logical summary of the contents of the frame, known as the CRC, or the cyclic redundancy check. Okay. Now this value is placed in the FCS, or the frame check sequence, to represent the contents of the frame. In the Ethernet trailer, the frame check sequence, or FCS, provides a method for receiving node to determine whether the frame experienced transmission errors. Okay. Okay, so layer 2 addresses. Layer 2 addresses is also known as the physical address. When you hover the physical address, that pertains to the MAC address. Okay, so the data link layer provides the addressing used in transporting a frame across a shared local media. So device addresses at this layer are referred to as the physical addresses, or MAC address. Okay, so data link layer addressing is contained within the frame header and specifies the frame destination node on the local network. It is typically at the beginning of the frame. So the NIC can actually determine if it matches its own layer 2 address, okay, before accepting the rest of the frame. The frame header may also contain the source address of the frame. Okay? So unlike layer 3 logical addresses, which are hierarchical, physical addresses do not indicate on what network the device is located. Rather, the physical address is unique to the specific device. So a device will still function with the same layer 2 physical address even if the device moves to another network or subnet. So therefore, layer 2 addresses are only used to connect devices within the same shared media. Okay? That is on the same IP subnet. Now, the figure here illustrates the function of the layer 2 and layer 3 addresses. Okay, so as the IP packet travels from host to router, okay, so in here, host to router, it is using a layer 2 protocol data unit. Okay, and therefore, NIC to NIC is operating on the layer 2 or data link layer, and that layer 2 frames has the destination and source MAC addresses. Now, once it reaches the router, okay, the communication now is on layer 3. Okay, this is now a layer 3 communication, and that is where IP addresses are being used. So we are going to discuss this process in detail on the next slide. Okay, so basically what will happen is, if we are going to move data from the source to the web server, which is the final destination here, okay, so your data goes into several encapsulation process. All right, so first, the source encapsulates layer 3 IP packet in a layer 2 frame. In the frame header, the host adds its layer 2 address as the source and add the layer 2 address of the R1 as the destination. Okay, so take note that we are working only on this area here. So the host will put its source MAC address, okay, and also it will have to place the destination MAC address, which is the MAC address of the R1's interface connected to the host. Okay, next, so we are now on a layer 3 communication. So it's a communication between R1 and R2. We call it router to router communications. So R1 encapsulates layer 3 packet in a new layer 2 frame. Okay, so it is a new encapsulation here. The encapsulation here is already done. We're done with it. And therefore, R1 will re-encapsulate the packet in a new form. Okay, layer 2. Okay, so R1 adds its layer 2 address as the source, okay, and layer 2 addresses of R2 as the destination. So if you will observe, when we're talking about the layer 2 addresses, okay, it is limited within the local connection. So if we're talking about the host to the R1, source is host, destination is R1. Okay, if the communication now is R1 and R2, source is R1 NIC here, and destination is R2 NIC there. Okay, so every hop, the source and destination MAC addresses changes. All right, so the third phase would be from R2 to the final destination or the web server. Okay, so R2 encapsulates the layer 3 IP packet in the new layer 2 frame. Okay, now again, this is a layer 2 frame. The source MAC address is that of R2, and the destination MAC address is that of the web server. All right, the data link layer addresses or address is only for a logical delivery. So addresses at this layer have no meaning beyond the local network. So compare this to a layer 3, where the address in the packet header are carried from the source host to the destination host, regardless of the number of network hops along the route. Okay, so on this diagram here, on our demo diagram, okay, the source and destination MAC address changes every time we go into a different hop. Okay, but the source and IP address remains the same throughout the process. Okay, so if the data must pass onto another network segment, an intermediary device such as a router is necessary. Okay, take a look at this. This PC here is at 192.168.1.110. Okay, the server is at 172.16.1.99. So they are located on two different subnets, and therefore we have to use a router for them to communicate with each other. Okay, now using the IP address, the router can determine the network location of the destination device and the best path to reach it. So when it knows where to forward the packet, the router can create a new frame for that packet, and the new frame is sent onto the network or to the next network segment towards its final destination. All right, so router is intelligent enough to do that. Okay, so the last one is LAN and WAN Frames. So Ethernet protocols are used by wired LANs. Wireless communications fall under the wireless LAN or the IEEE 802.11 protocols. So these protocols were designed for multi-access networks. So WANs traditionally use other types of protocols for various types of point-to-point, hub-and-spoke, and full mesh topologies. Some of the most common WAN protocols over the years have included PPP, HDLC, okay, frame relay. You've got the asynchronous transfer mode or ATM, which is not listed here, okay, and you also have the X25, okay. Now, these layer 2 protocols are now being replaced in the WAN by Ethernet, okay. In TCP/IP network, all OSI layer 2 protocols work with IP at OSI layer 3. However, the layer 2 protocol used depends on the logical topology and the physical media. So each protocol performs media access control for specified layer 2 logical topologies. This means that a number of different network devices can act as nodes that operate at the data link layer without implementing these protocols. Okay, so these devices includes the NIC on the computers as well as the interfaces on the routers and layer 2 switches. The layer 2 protocol that is used for a particular network topology is determined by the technology used to implement that topology. So the technology used is determined by the size of the network in terms of the number of hosts and the geographic scope and the services to be provided over the network. So a LAN typically uses a high bandwidth technology capable of supporting large number of hosts. The relatively small geographic area of a LAN or a single building, for instance, or a multi-building campus, and its high density of users make this technology cost-effective. However, using a high bandwidth technology is usually not cost-effective for WANs that cover large geographic areas, such as cities or multiple cities, for example. So the cost of the long-distance physical links and technology used to carry the signals over those distances typically results in a lower bandwidth capacity. So the difference in bandwidth normally results in the use of different protocols for LANs and WANs. So data link layer protocols includes this Ethernet 802.11 wireless, right? Point-to-point protocol or PPP, the high-level data link control protocol or HDLC, and frame relay. But frame relay is becoming obsolete, okay? And it is being replaced by any other technologies available. Okay, so each protocol performs media access control for specified logical topologies. All right, so we have reached the end of the video lecture. Have a great day. Thank you for listening and watching. See you on the next video lecture.